To introduce and motivate the study of the analysis of algorithms, we're going to talk about a problem called cardinality estimation. But before beginning, I just want to talk for a second about Don Knuth's legacy, the analysis of algorithms. We've known since Babbage that computational resources are limited, and the method and the algorithm that we use matters. Even Babbage, in his analytic engine, worried right from the outset to solve a particular problem, how many times were we going to have to turn the actual physical crank to get the computation done? What we're doing is not so different than that. And what Knuth's insight was in the 1960s is that analysis of algorithms really is a scientific endeavor. We start with a working program, an implementation of an algorithm. We develop a mathematical model of its behavior. We use that model to formulate hypotheses on how much time or space the program might take. And then we use the program to validate those hypotheses. Or maybe they give us an idea on how to change things or some other insight in solving the problem. So we iterate the process, developing ever and ever better algorithms and programs. And Knuth expressed this insight in his series of 4 volumes with more to come. I think it's very difficult to overstate the significance of this insight. Before Knuth came along, people were really very confused and expressing confusion about whether it would be possible for us to really understand how computer programs would behave. But with Knuth put this stake in the ground and many people followed, we really do have an ability to proceed as scientists to further our understanding of how computers and programs operate. And it really has played a critical role in the development of the computational infrastructure. At the very beginning, we had programs like compilers and assemblers that would translate from a human language into a machine language. But the running time of those programs definitely had an impact on how complicated how complicated problems programmers could solve. And for a lot of the first computers were used for things like cryptanalysis. And again, the analysis of algorithms really played an important role in understanding how big or how difficult a cryptanalytic problem we could solve. When we started with very large-scale integrated circuits, a good algorithm actually played a role in our ability to scale these circuits. And companies that didn't use such algorithms went out of existence, and the others became the huge companies that we know today that build our circuits. But it's not just that, also the advance of scientific knowledge. The famous n-body problem research on that was slowing to a crawl for a long time because nobody knew a good algorithm for doing large numbers of bodies. And similarly in bioinformatics and many other applications, analysis of algorithms has played really a critical role. And the way Knuth put it in the introduction to our book, Analysis of Algorithms, is this: people who analyze algorithms have double happiness. They experience the sheer beauty of elegant mathematical patterns that surround elegant computational procedures. Then they receive a practical payoff when their theories make it possible to get other jobs done more quickly and more economically. So we're fortunate to really start our story with this background. In modern times, this is 50 years or 60 years after Knuth's insight, I want to just lay out the context a little bit because it'll become important later on in the story. So we have people that are developing real code on real machines. That code is thoroughly validated and debugged. They work very hard to make sure that it's going to work well on those real machines. But generally, the applications and systems are pretty complicated, and the math models used are pretty limited in many practical applications. We also have a burgeoning theory of research on the theory of computing. And there they're working in the realm of abstraction, as Whitehead put it. They're talking about theorems, they're talking about abstract math models, and generally researchers in this field don't do very much experimentation nowadays. They're purely working in the abstract. In the analysis of algorithms in analytic combinatorics, we work with both theorems and code. That's what characterizes our work. We use Knuth's scientific approach, and we experiment, validate, and iterate much in the same way that physicists, biologists, or chemists might. So that's the context that I'm going to draw out through this story. So the case in point that we're going to talk about is a problem called cardinality counting. In a given stream of values, how many different ones are present? The reference application that we'll use throughout is this idea of a web log. So this is the people that downloaded pages from our website. They're strings, long strings, and they might be very long. This is, I think, a day's worth, maybe a month's worth, 6 million strings. Nowadays, these things could be billions long or more. And it's a standard interview question now. If you go to a modern company, they ask you how to solve a problem, and a lot of people will use this one as a problem. Give a stream of values, how many different values are present, how are you going to solve that problem? So that's the problem that we're going to address now. So the first answer, that naive answer that a beginning programmer might think about is check every value. So the idea is you save all the values in an array. When you get a new one, you check all the previous to see if that new one is there. And if not, you count a new value. And this code is extremely simple. And here's what it looks like. So we'll read all the data, and then we'll just go through the data. So that's an array with the data in it. And for every new entry, we'll go check all the previous entries. And if we find an equal one, we go out. And if we're not at the end, then we increment the count. That one's new. And then we'll just print out the number of different values. Why do I say that's the wrong answer? Well, it's the wrong answer because it's too slow. The running time is quadratic. It's not feasible for a real-world application to run a quadratic algorithm when your input is of length millions or billions. So anyone that answers check every value is not going to get to the next stage in the job application process. There's a standard answer that's been known for a long time, and that one is sort and then count. So in that one, you save all the values in an array, sort the array. That's a standard facility in any computer system nowadays. And what that does is it put equal values together in the sorted input, and then you can just go through and count the first occurrence of each value. So here's a small example of that process. Those are our values. We sort them. And then we just work through the array and just count the first instance of every equal value. So we start out with 6 different ones, but now we go for a while with the value that we have is equal to the one before it, so we don't increment the count. So we only increment the count when the current value differs from the previous one, which is an easy test. And then in this way, we found out there's 11 different equal values in this example. Sort then count. And again, this is pretty easy to code up in most programming environments. Just sort the thing, then keep a count, and if it's different than the previous one, increment it. In this method, it's been used for decades in all different types of environments, and you still find it in use in various systems. So in Unix since the 1970s, you basically use this method with the -u flag. And we actually use it for our first programming exam. Once beginning programmers know about arrays, we have them implement this. Usually their code is a lot longer than this 6-liner. So there's another method that some people think of called an existence table. So and this one works if the values are positive integers less than some constant u. So what we do is use what's called an existence table, where we create an array of true-false values. And when we get a value I, we just set b of I to true, and then at the end you count the number of true values. So here's our small example. When we see 15, we set a 15th entry to true. We see 9, we set a 9th entry to true. We see another 9, it doesn't change things. We see 4, and so forth. So every time we get a value we haven't seen before, then we get a new true in the existence table. And if we get values that we have seen before, nothing changes. And at the end, our number of distinct values is the number of true values in the existence table. I put an X on this one, and you might want to think about why. And the reason is that, take our reference application, we have long strings. The value of u would have to be prohibitively large, would have to be huge. A string of 256 characters would be 8, 2 to the 256 times 8 would have to be some incredibly huge number. You can't use an existence table if you have a large number of possible values. But there is a standard answer that you probably have thought about if you had an undergraduate course in algorithms, and that's hashing with separate chaining. So that one, you create a table of a smaller size that you can afford, M, and you transform each value into a table index that is random in a certain sense. So an example, and that's called a hash function, and what you might do is take whatever your value is, it's a pile of bits, treat it as a number, multiply by a prime, take the remainder after dividing by m. That's a simple example. There's many more sophisticated ones known. And then you make a linked list. Your table is a table of linked lists, and you put the colliding values in a linked list, and then you can go through those linked lists, ignore values already in the table. So here's our, again, our example data stream. There's a hash table. So for every value, we're going to compute a hash value, which is a number less than 6. In this case, we'll multiply by 97 and take the remainder and dividing by 6. So for 15, the hash value is 3. That means 15 goes on list number 3. And for 9, it's 3, and that goes on the same list. So we don't have to check everything in the table. We just have to check the ones that are in the same linked list. And then, so what the hash values do is divide the possible values up into m different categories and greatly limit the number of things that you have to look at. So after a while, so 6 hashes to 0, so it goes at the end of list number 0, and so forth. And then during this process, you can efficiently check for equal values and then just increment the count if you don't have an equal value. Now there's a key technical idea, algorithmic idea, is that we're going to keep the list short by doubling the table every now and then. And with all of that, we have an efficient solution to the cardinality estimation problem. And it's a classic problem in the analysis of algorithms is how much time does this process take? It's a very well-studied textbook method. And it's hashing, just like sorting, hashing is available in our computational infrastructure. Java's got a class called hashset that implements hash tables. The add method adds a new value, and the size method gives the number of different values added. So the solution to cardinality counting is a 4-liner in a standard Java program. And again, analysis of algorithms, plays a role in our ability to categorically state that this is an efficient solution. What we say is, if the hash function uniformly and independently distributes the keys in the table, then we know that the expected time and space cost is linear. It's just a constant times the number of items that we have. And if you look at our algorithms book, page 466, or if you looked in Knuth's books, you'll find a proof of this. It's based on classic probability theory using the binomial and Poisson distributions. Now, a question immediately arises. Do the hash functions that we use satisfy this? Are they uniform? Do they uniformly and independently distribute the keys in the table? And the answer to that question is it's not likely. We're using this idea of multiplying by a prime and so forth, maybe uniformly, but who knows about independently. But by making that assumption, we can prove a theorem and we can develop a hypothesis that we think the expected time and space cost is linear. And that's where scientific validation comes in. So now what we're saying is we have a hypothesis that the time and space cost is going to be linear for whatever hash function we're using and for whatever data we happen to have. And so we'll just do a quick experiment where if we have a problem of a certain size, if we double the problem size, the running time should double. That's what linear means. So here's some code to do this. Again, in the analysis of algorithms, we work both with code and with theorems. This is Java code that's going to be similar to later Java code that we'll do. So we get the problem size from the command line, initialize the input stream, get the current time in milliseconds is a Java method that we can use. And then we have this count method implemented on the previous slide using Java hashset class. And then we can take the time after we've done that, that's now, and then it's in milliseconds, so we take the difference and divide by 1,000 and print out the elapsed time. So that's a fine program that we can use to test the hypothesis that it's linear. And this takes our input and takes the first 2 million entries in the input and runs this method. So out of the 2,483,000 are different, and it takes 3.3 seconds. Now we can run it for 4 million, now there's, out of the first 4 million, there's 883,000 different ones, 6.55 seconds. That's about double. And we'll go one more time to 6 million, the full data, and about 1 million of them are different, 9.49 seconds. So that's running a lot of data through a lot of hash functions and a lot of calls to count, and I'm going to say that that validates the hypothesis. So, by the way, the sort-based method takes about 3 minutes, so we already have a much faster method than the sort then count method. So we have an algorithm, we have a mathematical model, we have analysis, we have a hypothesis about the running time, and we have code that validates the hypothesis. So the question is hashing with separate chaining effective? And the answer is absolutely is. It's validated in many, many applications, not just this one, for more than 50 years. So here's a summary of the algorithms that we've talked about for cardinality counting. The wrong answer is quadratic, can't be used in practical applications. Sort and count, we didn't talk about it, but the running time is n log n. It has to store them all in the memory. Existence table is no good because U might be huge. And hash table, even with these asymptotic bounds, achieves optimal. Now, there's an asterisk on it. Actually, even if the hash function is random, could be that it hashes everything to the same place, in which case the running time would be quadratic in the worst case. So in a purely theoretical sense, hashing doesn't guarantee to solve the problem. But making this uniform hashing assumption that it uniformly independently distributes the keys, then we can say that the solution is linear in expected time, and not only that, it's extremely likely to be linear. We can show much more about the distribution. And then scientifically, we can validate and have validated for a long time the hypothesis that this solution is linear. So pretty good answer to the interview question, which a lot of other people will give eventually, is go ahead and use a hash table. The question is that the end of the story? And for this lecture, the answer is no. It's really just the beginning of the story. So one problem, or really a fundamental problem, is that exact cardinality count requires too much space. Generally, the streams that we're talking about is much too big to be able to save all values in memory. So that's the first question the practicing programmer is going to ask. I've got, in my example, 6 million things. I could have 1 billion things. What do I do? And I just can't afford to save them all in memory. Well, the bad news is that you can't get an exact count unless you store them all in the memory, because maybe the one that you left out was different. In 1970, there's a thing invented called the Bloom filter that says you can get a really good estimate. You don't have to save the whole thing. If you save a few bits per distinct value, which is way less memory, you can do better. But what we're going to see in this lecture is much better news, that you can get a very accurate estimate using only a handful of bits. And that's really what our topic is for this lecture.